Okay, this video is going to be about the confusion matrix, which is at the heart of classification metrics. I've decided to put the reference at the top so that we don't forget where some of this information is coming from. I had to put in a caveat. There appears to be some contention whether false positive rate or false negative rate equals specificity or sensitivity or not. Depending on the interweb, whether it's a paper, a blog post, or even a book, there's some contention as to whether or not those things actually equal each other. So, for instance, from the reference, it says right here. Let me get to it. Where is it? Okay, from the reference, false positive / negative rates are often confused or conflated with specificity or sensitivity, even in publications and software. And we're going to see this a bit later on as we get into some of the metric charts. But for now, let's just move on to the confusion matrix, which is again at the heart of classification metrics. So here's our confusion matrix here on the left hand side. We have truth on the column side and predicted on the row side. Sometimes you'll see these interchanged with truth here on the row side and predicted on the column, but this seems to be a more accepted way of presenting confusion matrices. So this is just a sample of numbers within a confusion matrix, and then on the right hand side, how do these numbers correspond to the error classifications. So for instance, 65 is a true negative, 8 is a false negative, 12 is a false positive, and 92 is a true positive. And I also decided to color code the truth and the predicted portions. So in this column right here, 65, we predicted a 0 and it was a 0, therefore it's a true negative, because 0 is the negative outcome, 1 is the positive outcome. And then on the where the ones intersect, we have the true positive. We predicted a 1 and the truth was a 1. And then similar for the other diagonal, we predicted a 0 but it was actually a 1, so it's a false negative. And then here is we predicted a 1 but it was actually a 0, so it's a false positive. And then just here on the right hand side, quick area for some manual calculation of some of these metrics. So there's an input text box on the far left. We can enter in our true negative, true positive, false negative, and false positive. We send it through the formula tool, and then we get our various metrics here on the bottom or on the left hand side. Okay, continuing on, we'll look at 6 matrices. First is the F1 score, then accuracy, specificity, also known as accuracy 0, sensitivity, recall, accuracy 1, precision, and prevalence. So the F1 score is the model accuracy on the dataset. It is a balance between precision and recall, and it can help the rare class issue. And below that we see the formula. And as we can see, it is a balance between precision and recall. Below that is the accuracy, which is the accuracy on all the predictions. We can see that, or it's also often described as diagonal accuracy because it's this diagonal here. It's all the correct predictions, the true negatives plus the true positives over all predictions, as you can see here, the formula. We also have specificity, which is the accuracy of predicting a negative outcome. It's also known as the true negative rate, and the formula below that as well. And I've added the truth perspective on it because what that is here is this column perspective, so to speak. It is true negative divided by true negative plus false positive, so it's a truth perspective. And then next to that is sensitivity recall, also known as accuracy 1, at least in Alteryx's labeling, which is the accuracy of predicting a positive outcome, also known as the true positive rate. And that formula is true positive divided by true positive plus false negative. Again, a truth perspective in that it is on the column. And I added that because the next metric is precision, which is the accuracy of predicted positive outcomes. And this is a predicted perspective. So if we look at the formula, we see it as true positive divided by true positive plus false positive. So it's true positive on the predicted perspective, which means it's going this way, right? So precision is looking at true positive on the predicted perspective, while sensitivity and recall is looking at true positive from the truth perspective. It's two different perspectives here, so it's important that we kind of distinguish it. Precision is another way of saying it is that of the predictions made, how many were accurate. And then last we have prevalence, which at least I haven't come across often, if at all, but it is a measure of the balance of the data within the data set, the population. And last on this particular metrics section is, when do we use precision or when do we use sensitivity? Because as you can see, they're both measures of true positivity, right? True positive, and the only difference is, well, on precision we see that FP, or false positive, is important. Sensitivity, false negative, is important. So precision or sensitivity, oftentimes there is a spam email versus fraudulent transaction example, because it's quite easy to actually understand with these two examples. So spam email, that's something we want to detect, but it's often going to be somewhat imbalanced. Same with fraudulent transactions. There'll be many transactions, but perhaps not too many fraudulent. So precision, false positive, is important because we don't want to lose important emails. And then conversely, sensitivity, we have false negativity is important because a bank or a client doesn't want to lose money. So depending on a situation, we may want to focus on precision or sensitivity and kind of move away from accuracy, because accuracy may not always tell the whole story. It may not be the important thing to model. And moving into that last section is going to be our chart metrics. We'll look at 4 of them. Quickly looking at lift curve, gain chart, the PNR curve, and the rock curve. So first is going to be our lift curve. Let's get this in view. Okay. Lift curve is the effectiveness on the y-axis of predicting ones at different probability cutoffs, x-axis. It's most or more important in rare case problems where perhaps the default 0.5 cutoff can be adjusted to avoid having too many or all records classified as 0. And this particular example, this was a fairly balanced data set. By lowering the cutoff, a lift multiple or gain over random chance can perhaps be realized. So even on this fairly well balanced data set at 0.5 cutoff, we had a gain of about 1.6, so doing quite well over random chance. And then something similar, kind of complementing this particular chart, is the gain chart. It shows something quite similar, and they were also plotting the rate of positive predictions on the x-axis, but this time we're plotting TPR, true positive rate of sensitivity on the y-axis. Now we're seeing something similar. 0.5 on the lift chart was quite a nice gain, and here at 0.5 we're showing clearly well over 0.8% accuracy. Next is our PNR curve, our precision and recall curve. This is quite an interesting curve because one of the things you'll notice here is that precision starts at 0.5, but let's go to the definition to see why it's interesting, because what we're plotting is sensitivity recall against precision, and definitionally speaking we're plotting the accuracy of predicting a positive outcome against the accuracy of having predicted a positive outcome. So quite an interesting chart. And finally, the granddaddy of classification, or at least two-class classification, that actually has to be put in there. Two-class classification is the ROC curve, which stands for the Receiver Operator Characteristics Curve. It's the model's ability to correctly identify ones without misclassifying zeros as ones. It displays the trade-off between specificity on the x-axis and sensitivity recall on the y-axis. And this is partly where the caveat comes in, because this is labeled through the software as false positive rate, when depending on your source it would actually say that this is the true negative rate. But this is perhaps the time where you would probably make a note, and you would have to take this up with experts and other folks that are much better versed in this particular terminology. Continuing on, the dash line, which splits the chart diagonally, right? This indicates the 50-50 or by random chance effectiveness of the classifier. So we are clearly doing much better than 50-50. And again, we want to be in the top left of the chart. Also, it includes the AUC there's often AUC metric, the area under the curve, which is a measure of the classifier's effectiveness. This is only for two-class classifications though. So again, we want to be in the top left because what we're doing here is we are correctly identifying ones through the true positive rate measurement, without misclassifying zeros as ones if we are truly in the top left of the ROC curve. Okay, so that is pretty much a fairly quick, slightly deeper rundown of the confusion matrix. So until the next time.